This is a tooth the size of your hand. And this is the animal it came from. About 15 million years ago, in the warm oceans that once covered most of the planet, something was swimming beneath the surface that had no real rival. Its jaws alone could have swallowed a person whole without much effort. Its bite may have been the strongest of any animal that ever lived. This is Megalodon, the largest shark to ever exist, and quite possibly one of the most powerful predators in the history of life on Earth. And I want to be careful with the word here, because it's the thing almost everyone gets wrong about this animal: complete. We talk about Megalodon like we know it, like there's a skeleton in a museum somewhere that settles the question. There isn't. Almost everything you've ever seen of this animal, every reconstruction, every documentary, every viral image comparing its jaw to a school bus, is built from a body part that makes up a tiny fraction of what the animal actually was. Because sharks don't fossilize the way other animals do. Their skeletons aren't bone. They are cartilage, soft, flexible tissue that breaks down and disappears long before it has any chance of turning to stone. What survives, almost every single time, are the teeth. Hard, enamel-coated, built to be replaced by the thousands over a shark's lifetime, and built, as it turns out, to outlast almost everything else about the animal that once carried them. So the question this raises is a strange one. How do you reconstruct one of the largest predators in Earth's history from a pile of teeth and almost nothing else? Megalodon lived from around 23 million years ago to somewhere close to 3.6 million years ago, across an enormous stretch of time we call the Miocene and into the early Pliocene. That's over 20 million years as one of the ocean's dominant hunters, longer than most predator lineages managed to survive at all. Its teeth have turned up on nearly every continent: in Africa, in the Americas, across Europe, in Australia, buried in seafloor sediment that once sat beneath shallow, temperate coastal waters. Wherever the ocean was warm and full of prey, Megalodon appears to have been there. But when the species disappeared, it left almost nothing behind except those teeth, scattered across the world in almost unimaginable numbers, and settled into rock and sediment for millions of years. The first of those teeth were found long before anyone understood what they actually were. For centuries, huge triangular fossils turned up in coastal cliffs and riverbeds, and people had no framework at all for what they were looking at. In parts of Europe, they were called tongue stones, thought to be the petrified tongues of dragons or serpents, and were sometimes worn as charms against poison. It wasn't until the 1600s that a Danish scientist named Nicholas Steno examined one of these tungstones closely, dissected an actual shark's head for comparison, and realized the fossils were teeth. Shark teeth, but on a scale that made no sense for any shark known at the time. It took nearly 2 more centuries before the species was formally described. In 1843, the Swiss naturalist Louis Agassiz gave the animal its scientific name, Carcharodon megalodon, meaning big tooth, built on comparisons to the teeth of the great white shark, which at the time was thought to be its closest relative. That single decision, linking Megalodon to the great white, would go on to shape almost a century and a half of how we pictured the animal, and much of that picture we now think was wrong. Because here's the problem. A tooth tells you a great deal, but it does not tell you everything. It can tell you roughly how an animal bit, what kind of prey it could tear through, sometimes even how fast it grew. What it cannot tell you, not directly, is the shape of the body that tooth belonged to. And for decades, scientists filled that gap the only way they could, by assuming Megalodon looked like a scaled-up great white shark. That assumption produced the image most people still carry today. A colossal, thick-bodied great white, just enormously bigger. It's the version used in documentaries, the version stitched into comparison charts next to buses and whales, the version that shows up whenever someone tries to imagine what it would be like to see this thing coming toward them in open water. But that assumption started to break down once scientists looked more closely at where Megalodon actually sits on the shark family tree. It isn't a close relative of the great white at all. The two evolved their similar tooth shapes independently. A case of convergent evolution, the same solution to the same problem, arrived at twice, separated by tens of millions of years. Megalodon's actual lineage traces back to an older group of sharks, and its closest relatives suggest a body plan that may have looked meaningfully different from a great WAA. But that assumption started to break down once scientists looked more closely at where Megalodon actually sits on the shark family tree. It isn't a close relative of the great white at all. The two evolved their similar tooth shapes independently. A case of convergent evolution, the same solution to the same problem, arrived at twice, separated by tens of millions of years. Megalodon's actual lineage traces back to an older group of sharks, and its closest relatives suggest a body plan that may have looked meaningfully different from a great white's. Possibly a longer, more slender snout, different proportions through the body, a different overall silhouette entirely. This is where the honesty has to be sharpest, because we have never found a complete Megalodon skeleton, not one. What sharks leave behind, aside from teeth, are occasional fragments of calcified cartilage from the spine, vertebral centra that sometimes survive where the rest of the body does not. A handful of these vertebral columns have been found, one remarkably complete set discovered off the coast of Belgium, and they've let scientists estimate things like overall length and, more recently, challenge some of the assumptions the great white model had baked in. But a spine is not a body. It tells you about length and maybe girth. It does not hand you the shape of the fins, the exact taper of the tail, the true profile of the head. Which means the reconstructions you've seen, however detailed, however confident looking, are still built substantially on inference, educated inference, tested against the physics of how large aquatic predators move and against comparisons with living sharks, but inference all the same. And the same honesty applies to the number everyone actually wants to know. How big was it? The earliest estimates, some of them dating back over a century, pushed Megalodon's length past 100 feet, treating it as an almost unimaginable sea monster. Those figures were based on a flawed method, scaling up the whole body using tooth size alone, compared proportionally to a great white's tooth-to-body ratio. It felt reasonable at the time. It also happened to be built on the wrong reference animal. As the science matured, and as more complete tooth sets and those rare vertebral remains entered the picture, the estimates came down substantially. Most current research places Megalodon somewhere in the range of 50 to 65 feet in length, with some analyses suggesting the upper end of that range for the largest individuals. Still an almost incomprehensible size for a predator, roughly 3 times the length of a large great white, but nowhere near the 100-plus foot figures that circulated for so long. The animal did not shrink. Our measurement of it got better. That single idea might be the entire story of Megalodon science compressed into one sentence. Every generation of researchers built the best model the evidence available to them could support, and every generation after found new evidence that forced a correction. The teeth got studied with better imaging. The vertebrae got scanned instead of just measured by hand. Growth rings inside the cartilage, similar to tree rings, started revealing how fast individuals grew and how long they likely lived, with some estimates suggesting a lifespan that could stretch beyond 80 years and a body that kept growing for most of it. Even Megalodon's diet has been rewritten more than once. It was long assumed to have hunted the same modern-style whales we see today, but the fossil record tells a different story. During Megalodon's reign, the oceans were full of smaller, slower whale species. Along with seals, dolphins, and large fish, an entire ecosystem of mid-sized marine mammals that no longer exists in the same form. Bite marks preserved on fossil whale bones, some of them crushed clean through, suggest an animal capable of demolishing prey other predators couldn't touch, and possibly one that targeted the chest cavity of its prey directly. A hunting strategy inferred from exactly where those bite marks tend to appear. Why it went extinct is still argued over as well. For a long time, the popular explanation involved a single dramatic culprit, whether climate cooling, competition from other predators, or the rise of a rival at the top of the food chain. The current picture looks more layered than that. Sea levels dropped, coastal nursery habitats where young Megalodon likely grew up in shallower, safer water, began disappearing. Ocean temperatures shifted as the planet cooled heading into the Pliocene, and the very prey species Megalodon depended on were themselves declining or evolving to move faster, dive deeper, grow more elusive. It wasn't one door closing. It was several at roughly the same time. Which brings this back to the question that started it. How can we describe, with any confidence, an animal we have never fully seen? An animal that left behind teeth by the millions and almost nothing else? The honest answer is that we can't, not completely, and serious researchers don't pretend otherwise. The Megalodon described today, the one with the more slender build, the corrected size range, the reconsidered hunting strategy, is the best reconstruction the current evidence can support. Built from fragments, tested against the mechanics of how enormous predators actually move through water, compared against the bodies of the living sharks that remain. And ready to be rewritten again the moment a better fossil comes out of the ground. That isn't a weakness in the science. It's the only honest way to describe something this size, this old, and this thoroughly gone